This is an example of a pretty classic control system. This is a triple pendulum, but you learn to like control this thing to swing up and stay stable. So a lot of the methods you guys will study kind of can solve these kinds of systems. All right, so some logistics. Homework 2 is due on Tuesday. Got hardware issues. It's okay, take some more time, no problem. Homework 3 should be out on Wednesday. Homework 3 is about control. And I'll put out a EdSTEM discussion page. You have a week, just like add some thoughts on the presentations, suggestions, feedback, things that come to mind from the papers, right? Make sense? Okay. Two more pieces of logistics is Tyler. My postdoc is gonna lecture on Wednesday. He's great. He's a control theorist. He knows more control than me. So that'll be good. The other thing that came up recently, which is more of a thought to run by you all, is Peter Stone, who's like a CS professor of robotics from UT Austin, is gonna be our colloquium speaker on Friday. He's like a world expert in multi-agent robots and robot soccer and this kind of stuff. We could, the problem is that it overlaps with our class. And so we could just do lecture as normal. We could also do like a guest lecture where we just like all go to his talk. How do we feel about that? Is that something we want to do? Do we want to just do the con is that it puts us behind on control. And so that makes things harder. Right? So like, but it's a democracy, right? So let's how do we feel about this? Do we want to go to Peter's lecture? Do we want to do our lecture? How do we want to go about this? Yeah.
Thanks. Just do the lecture as normal because these are recorded anyway.
Yeah, I agree. Okay. Anyone object to that? We'll just, yeah. It would be interesting. My concern is that it puts us significantly behind. It puts us like, because it's the weekend, it puts us like further behind for you all to be able to start the homework. And so that's my main concern. Here, how about this? We have some really great speakers in the winter. We have another one from Stanford and MIT later in the quarter. How about we do a guest lecture for those ones when we're like further along in the course and you guys can listen to Peter Stone's recorded lecture. Is that cool? Yeah? Everyone okay with that? I mean, I don't know why they scheduled it this way, but this is how it is. Okay. Any other questions before we keep going? Good. All right. So quick recap. We talked about the Kalman filter. The Kalman filter is a Bayesian filter, which is linear and Gaussian. Then we talked about the dynamic step and the measurement step. And then we said, okay, well, the world is not linear and Gaussian. So how do we go from there? We use the EKF, and the EKF tries to do a Kalman filter, but does linearization, right? So it takes a nonlinear dynamics, linearizes it using the Taylor expansion, takes a nonlinear measurement, linearizes it using a Taylor expansion, and then just uses the same machinery as a Kalman filter. The only difference is that every time you're dealing with the system, you have to relinearize it because the linear approximation is only valid for a certain period of time, right? Or certain region. So the difference in the EKF and the KF is that they're both Gaussian, but the EKF can deal with nonlinear dynamics. Okay, and so what we learned is we started with the particle filter, right? So we said we're going to deal with the particle filter, which is nonlinear, non-Gaussian. We then went back to the linear Gaussian case of the Kalman filter, which is closed form. And we went back to we went forward to the extended Kalman filter, which can be nonlinear, but still Gaussian, right? So in practice, the particle filter is a great choice because it's easy to implement, easy to scale, and it's nonlinear, non-Gaussian, right? So especially with like GPU parallelization and stuff, you can, for instance, push things forward through the particle filter really easily, which I think is a plus. Okay, so one thing that we haven't talked about is we've been talking about like known maps, right? So if you look at the homework that you all did or are doing, the map is given. Someone does the mapping for you. But in most cases, you don't know the map, right? So in most cases, the map is not known. You have to kind of figure out the map as you're going around things. So like, for instance, you're trying to go around these obstacles. You're trying to figure out where the obstacles are as well as where the robot is. And so this is a problem called simultaneous localization and mapping, or SLAM, right? And SLAM is basically a filtering problem where you're trying to do inference over not just the robot's position, which is what we've been doing so far, but also over the map, right? So you're given the controls, you're given some observations of nearby features, right? You're still getting like LiDAR measurements, but what you're trying to estimate is not just the position of the robot, you're also trying to estimate the map. And so what we did so far is assume the map is known, use that to define the observation model. What we do here is that we try to treat the map and the position of the obstacles as things that we infer. Right? And so the SLAM problem is interesting because you have to jointly infer the map and the position of the objects. Okay, so why is SLAM difficult? Right. So in localization, what we did so far, we assumed that the map is known. We said where the only uncertainty is coming from the robot's position. But now you're saying that the map is not known, and you have to do both jointly. It's kind of like if I don't know where I am and I don't know where the map is, then I like kind of reading tea leaves a little bit, right? So SLAM as a problem is quite hard. But it's useful in lots of problems, right? It's useful in lots of settings. So these are some settings where people have already used SLAM. So indoor mapping, so like all of your Roombas do SLAM in some capacity, right? They map your house. If you ever see the Roomba map, it's from SLAM. Underground or undersea robots, things in space, things underground in like caves, all of them build a map of the world. Because how do you like navigate the world without a map? Unless you use learning-based methods, but SLAM tends to work really well, so you could form maps like that while you're moving around the environment. So generally, the definition of the SLAM problem is that you're provided the actions of the robot, you're provided some observations, which is what LiDAR measurements in different directions, and you are trying to do inference over the map of the environment, which is usually represented as a series of landmarks, and the path of the robot, which is like where is the position of the robot at any point of time. Right. And so the way you kind of solve it is through Bayesian filtering. You treat it like a Bayes filter. It's just that you expand the state. Right. So you treat it as the normal Bayes filter, but instead of just treating the state as the position orientation of the robot, you also include the position and orientation of the landmarks as part of your state. Right? And so you're doing inference over not just this, over the position of the robot and of the landmark. And so you can use the whole machinery from before, you're just expanding your state. And so we won't have time to go into EKF SLAM in detail, but the point here is that you're going to try and have your state space be something like X, Y, and theta, like it was before, but also include the position of all the landmarks. Right? So landmarks are like obstacles in the world or like special features you're trying to find. And so you're going to get X, Y, theta and position of all the landmarks, and you're trying to estimate a belief over this whole thing. Their belief is going to be like no longer three-dimensional, but 3 plus whatever, n times 2. And so if you want a more detailed version of this, look at my slides from CSE 571. I have like 2 lectures on it, but we won't have enough time to go over it. Kind of roughly what it's going to look like is that you start by doing the motion model like we did before. So it projects where the robot state is going to be. And then using the updated state, it's going to update the belief of where the landmarks are going to be, right? And then from that, it kind of like collects a measurement, updates both the robot state and the landmark state, and then repeats. And so you can kind of use a lot of the same machinery that we did earlier, and the results kind of look something like this, right? So this is navigating in Garage. And so you can use things like particle filtering, you can use things like EKF, like all of them will give you both the position of the robot and the landmarks of all the like pillars and cars and so on. And so usually a SLAM system will kind of drive in a loop trying to map through the whole environment. And what makes it hard is there's ambiguity, right? Like if you don't know where you are, you don't know the map is, 2 scenarios might look the same. And so that's why you often have to I know I always keep putting ads for different companies, but they have the best videos. But that is SLAM in 5 minutes. Lot to study in SLAM, but I'd recommend looking at 571. Yeah. Any quick questions on SLAM before we get to control? Alrighty, sweet. Let's do control. So what we're going to talk about for control is we've covered localization, right? We've talked about filtering and particle filters and common filters. Now let's switch from estimating where the robot is to controlling the robot. So we're going to try to think about how does control fit in our roadmap of building an autonomous system. We'll talk a little bit about what makes control problems hard, and then try to like come to a concrete instantiation of what a control problem is. Right? And so let's start by going back to the helicopter from lecture 2. Right, so we had this loop where we said we're going to have a world model. The world model tells you how the world works. It's a simulator, right? And then we said, well, the world model needs to know where the state of the robot is to predict what's going to happen forward. And that's what state estimation does. State estimation says, hey, well, given what you've seen, this is where we think the robot is. You can stick that into your world model. World model will tell you, given this is where you think you are, you take this control. This is where you're going to be in the future, right? What planning does is it says, given your world model and your state, like let's decide like a course plan of action. Like you need to like, let's say I'm going from here to the Ave. I like navigate to the fountain and then navigate somewhere near the red square and then cross the bridge and so on, right? So like planning kind of gives you a relatively coarse path. And then control is like what lets you control your joints to actually follow that path. And so the difference between planning and control is really like a granularity difference, right? But the methods are a bit different. So we're really going to think about control, which is saying that once you've done planning, you kind of know what path you want to follow. How do you follow that path? Under disturbances, under noise, under model error, right? And so it's saying that we're not going to worry about how the path shows up yet. We're just going to try and follow a given path, right? Okay, so generally we have the sense plan act paradigm. We've started by estimating robot state. Then you have to do planning to get a sequence of paths to follow, and then control, which is what we're going to do next, is trying to control the robot to follow a particular plan when you have disturbances or errors in your model. Right? And so we tried to solve this over the last couple of weeks. We're going to assume that planning is solved for now. We'll come back to it in a few weeks. And we're going to think about control. Right? We're just going to think about, given a path and an estimate of state, we're not going to worry about the state estimation. We're not going to worry about planning. We're just saying, given a state and where you want to go, how do I follow the path under some disturbances? Okay, so one way to think about control is that in state estimation, you were sitting in the passenger seat. You were saying that like the system is going to be driven, right? If you remember how we talked about it, is like the controls of the system were given. We didn't ever think about controlling the system. And so we said the controls of the system were given. And we're going to now move to the driver's seat. We're going to say, hey, we can actually control the system. What do we control it to do, right? And so it's kind of like from a passive sensing paradigm to an active, right? You want to act in the world. And so what do we get from control? Well, hopefully we can get things that look like this. This is like an extreme parking situation. That was kind of cool. So it's this car that's trying to reverse park. So this is what we expect in 2 weeks. So good luck. Yeah. So don't be afraid to push the musher cars to the max. Don't blow them up. All right. So what is control? So generally, control is saying that you have a plan. You want to figure out how to map to actuator commands under some set of disturbances in your environment. So you will assume that you know a model of the world approximately. But you're trying to figure out how to use that model of the world to achieve waypoints. But you're not going to do global planning. You're going to try to say you're going to achieve the next waypoint, which is local, short horizon. Right? And so we're gonna start by defining some notation, right? So we're gonna say, let's say our car at state x naught, y naught, theta naught, at time step t naught, right? You're gonna try and follow a plan which looks something like this, which is saying that at time t1, you want to be at x1, y1, theta1. At time t2, you want to be at x2, y2, theta2, and so on. Right? So you're trying to follow this kind of like path that goes from t naught to t3 and so on. Right? You're trying to track this path. And so we're going to try and do control problems that are tracking problems. And often you'll have like a helicopter, you have a charted path, you want to do it under disturbances, right? And so this is going to be called our reference trajectory. And a reference trajectory, the first way of thinking about it is at time step t, you want x to be something, y to be something, and theta to be something. Right? And so it's defined as a time-varying function of x, y, and theta. And we need to figure out what controls we'll feed into our system in order to accomplish this path. Yeah. Okay. So now the question is, why feedback? We're talking about feedback control, right? So when I say feedback, I'm talking about a system which acts, takes in its errors, goes back into the system, changes its behavior. Why feedback? Like, why not just say, hey, you know, model of the world, right? You know, the kinematic model we talked about, this like car rotation model. Why not just like choose the best U from there, choose a sequence of U's that accomplish a trajectory and just run them? Yeah. We deviate and then exactly, exactly. So the challenge with doing this kind of open loop control, like Martha was just saying, is that it's like just like that reckoning, your errors will keep accumulating, right? So you make a little error, you make a little error, you make a little error, and you end up way, way, way off. And so now it's harder to think about for like a Roomba, for instance, which is going really slow. But like imagine you're an F1 car and you're just playing things open loop. The driver is not touching the wheel. That's a scary situation, right? And so in general, the idea of feedback is that because your model is wrong, because there are unknown disturbances in your system, you want to use the errors that you make in order to correct for things. So you're like always correcting for little mistakes. And so if you look at the way like you drive, you like typically end up correcting a lot of your mistakes constantly. And so like most control systems are feedback control systems. And so by feedback, we mean things that use errors in your, like errors that you have experienced in order to affect your future behavior, right? And so that's often called closed loop control or feedback control. And open loop control is just saying, generate a sequence of controls and play them one after the other, right? So open loop control is typically bad. Closed loop control lets you deal with model errors, lets you deal with, changing systems and so on. Okay, so the idea of feedback control is saying that you measure the error between your current state, your reference trajectory, and you use that to kind of go back. Okay? So saying that you like deviate this way, you go that way, deviate that way, you go back that way. And the question is, how do we design a rule that goes between this error and how to control your system? And so the problem of feedback control is using this error in order to design how to take actions in the world. Yeah. So you have a reference trajectory you're trying to hit. You want to design a rule that goes from error to actions. That's the feedback control. Right. So one way of thinking about this, which is often useful, is to think about it as a vector field. Right. So it's like, well, if you're here, you would go here. If you're here, you would go here. If you're here, you would go here. Right. And so it's kind of like not saying what control to take. It's more like a rule on how to act depending on what your error is. Right? So it's kind of, if you're familiar with learning, it's kind of like a policy. Like a policy is typically closed loop, or it's just like you can think of it as like a set of rules which say how to map your error into controls that bring you back on track. Okay? And so, yeah. So a natural question is, we hear about control for the last 30 years. It's still a research program. Okay? Why is this still hard? So if you look at a system, in like a factory, right? So for instance, you have like a system that's trying to do packing or like assembly, but in like these nice clean cages. They often work really well, right? You don't have that many disturbances. Your system's pretty controlled. Your set of objects is known beforehand. And you don't really have to be that robust, right? So, well, you don't have to be robust, but you don't have to be that adaptive, rather. You don't have to really deal with lots of unforeseen things. So you do use feedback even in these systems, but they're like very controlled. Right? And so the thought here is that these systems make assumptions. One of the assumptions is that the system is fully actuated. You can control everything in the system perfectly. Secondly, there's very, very little execution error. You buy these like $200,000 robots, they repeat the same thing over and over and over and over. You go to the robotics lab, our robots cost $500, and then they make lots and lots of errors. So you can't be open. They don't cost $500, but more, not 200,000. And because the environment is controlled, you can kind of kill the errors and disturbances in your system. And because you like, it's a factory, you can control the factory. But if you're like Boston Dynamics and you're trying to get, your humanoid to jump and do backflips and do steps, right? That may be a significantly different system, right? So what makes it different? And so the first thing is that your system is not fully actuated. You can't control everything in your system perfectly. Like for instance, you're trying to pick up an object and you're trying to play tennis, right? You can't actuate the ball perfectly. It's like an inherently under-actuated system. So when you think of an under-actuated system, it's a system where you don't have direct control over all degrees of freedom, right? So like, for instance, right now, this thing is like fully actuated. I have full control over this clicker, right? But if I think about like a system where I'm like pushing this thing on the table, that's an under-actuated system. I like don't have full control over it, right? And so most systems in these kinds of like high performance environments are under-actuated, right? And so you can't just like teleport to where you want to teleport. You have to obey the dynamics of your system. The second thing is, or I guess under actuated systems, you have gravity, momentum, and so on. But you have to kind of use those in order to do a backflip. You can't just like directly set the system to where you want it to. The second thing is that you don't really know the model of your system perfectly, right? So like, for instance, in a helicopter, if you're trying to do, for instance, backflips with your helicopter, you can build models of your system in certain cases. But let's say you're like trying to do backflips in these extreme conditions. There's wind, there's drag, there's things like that. It's very, very hard to model those exactly, right? And so in most cases, your system is going to be approximate, which means that if you did planning through that system, it's inherently going to be wrong. Right? So it's like, if you just made a bunch of assumptions, you planned into the wrong model, you're going to get the wrong control, right? But the thing that makes feedback control so beautiful is that it's saying that wrong models can still be useful when used with like feedback that allows you to correct for model error, right? And so the idea is that you can make errors that you will fix in the future, right? And so unlike, it's like lazy optimization. You're saying that like I will be okay now because I can correct it in the future. And so you're never trying to be perfect in feedback control. You're just trying to be good enough. Okay? And so the point here is that even with an approximate model, simple model, if you have feedback, you can kind of get a well-behaved system. Right? So even if you have a system that is like behaving chaotically, as long as you're able to continuously correct for the errors, you'll get a well-behaved system. And so that's kind of the like basic premise of feedback. Does it make sense? Okay. So people will keep trying to build better and better and better models. I think that's maybe the wrong way of going about it. You want to build a model that's good enough to do control, right? At least in our cases, we don't care about modeling the system perfectly. We just care about it being good enough to control it. And feedback lowers the burden on modeling. So more you have feedback, the less well your model has to do. Okay. The third situation is that often models change on the fly, right? So I was at the DARPA meeting this weekend, and they were talking a lot about like robots that are in the field get damaged, and like what happens to them then, right? Here's an example I really like from some folks at Wyoming. It's like the spider robot that like gets damaged, but you can see that it like no longer can walk straight because it's damaged. The model has changed, but it like tries to kind of estimate how its model has changed and adapt it on the fly. And so in some ways that is a feedback controller. It's like feedback of what changed in the world and adjusting its behavior accordingly. And so systems will change on deployment. You deploy a robot for long enough, something will change. Feedback control lets you deal with these kinds of changing models. No. All right. So given that, let's think a little bit about how to ground this in real time, right? So we're going to say, let's try to follow a trajectory. We have a car, the state is X, Y, and theta. right? Same as we did before. Now you want to follow a trajectory. The question is, how do you parameterize the trajectory? The first thing we said is we have a time parameterized trajectory. And so we say that like at time step t, you want your system to be at x, y, and theta, at a particular x, y, and theta. So you have a time parameterized function that tells you exactly where your system is going to be at any particular time. Right? What might be the problem with this parameterization? Like why is it not perfect? Yeah.
Car is slower than expected.
Right. If your car is slower than expected, you have an unexpected obstacle. You're going to end up with this kind of like irreducible delay, and you can't really fix it, right? And so sometimes you really just care about following a path. You don't really care about getting there at a particular time, right? And so a second option here is to do, instead of time parameterized trajectory, you do like an index parameterized trajectory. And so rather than saying, I'm going to be at this state at this time, you just want things to be followed in sequence. Right? So you're saying that like, let's say you defined k different points in the sequence, right? You're saying, I just want to get to the next one. And after I get to this one, I want to get to this one. After I get to this one, I want to get to this one, and so on, right? So an index parameterized path doesn't care about time. It just cares about following things sequentially. Right? And so the nice part about this is that it kind of gets the geometry right. It follows the path you want to follow. The con is that it's slow. It may be slower or faster than you want it to be. Right. So great question. So the question is, what's the difference between tuning your control costs and using time parameter? Control cost plus index versus time parameterized, right? So one challenge might be, let's say you actually want your system to move kind of slowly in certain places and fast in other places. And so if you're time parameterized, you could say you really want to get through these things quickly and then these things fast. Whereas with a cost function, that might be a little trickier to get right. But it might not be that. Okay, so these are just design decisions you make in a system. Like let's say you're like a train and you really need to cross another train at a particular point in time, otherwise you're going to crash. Like you should probably be time parameterized. But if you're like a RC car in a little hallway, like probably better to be index parameterized, right? And so it kind of depends on your problem. But the way we're going to do this is we're going to start by first getting a path to track, right? Then picking a reference state. So let's say your path was like this, right? So, and your robot was, let's say, here. You want to find where you want to go to. That's kind of your set point or your goal, right? Or your the thing you're trying to get to, your reference state. You compute your error between your current state and your reference state. And then you try to think of a controller that'll get you back to your reference, right? So feedback control is typically take your path, find a reference state, take your current state, find the difference between your current state and the reference state, and then control your system to accomplish that. Okay? And so every controller is going to kind of make some choices that you get. So like, how do you parameterize a path to track? How do you choose which state to go to? How do you compute the error? And then how do you compute the control law to minimize this error? Yeah. Good. All right. So we talked about how to parameterize paths. The next question becomes, how do you choose a reference state? How do you choose where to go back to? So what are thoughts, right? So you have a path. Let's say you have like an index parameterized path. And your state of the world is now X, Y, and theta. How do you choose the reference state? How do you choose what to get back to?
Like minimum distance from the path.
Minimum distance from the path. Got it. So you first choose the first option is choose a single state that is closest to your current state, right? So you say you choose your current state is X, Y, theta. You try to choose an X and a Y from your path that has the minimum distance from your current state. So that's good in many cases. Why could it be bad? You can keep oscillating. Yeah, exactly. You can keep oscillating. The other option is if your like momentum is taking you this way, but the closest state is this way, you gotta like you go backwards, right? And so it's not always the best to choose the closest one. What's a different option?
Yeah. Could you one thing where you like draw like your Google Play, so it's like take the thing that.
Okay, so you're saying like take your current state at the endpoint and pick something where it intersects or something. That's a reasonable idea. I guess the trick, you might have the same thing where you like intersect, you have to like have a huge change in direction.
Yeah.
So maybe a different alternative here is like a little bit kind of in between, which is like look ahead search, right? Which is saying that you're XY, but we'll find another point, which is your look ahead point, right? Which is not the shortest distance, but which is like L steps away and ahead of your current time. Right. So this is like where you deviated from last. And you pick something that's ahead, which is like L steps away. Right? So you say, you don't want this to be the shortest distance. You don't want it to be 0. You want it to be some L steps ahead. Right? And so that often works well. I think that's what you'll do in a lot of your homework. Right. And then how are we doing on time? Okay. So I will leave Tyler to kind of tell you more about how to compute the error and feedback control. But I will see you all on Friday. Yeah. Cool. All right. Thanks. You're good. Thank you. I appreciate it. How do you think the presentations were? Do you think they were good? Like do you think they were constructive using class help?
I did.
So dynamics time you have to like also have I was just like rejected through like noise. Dynamics Sorry, I'm not sure. But it still helps to look ahead because you don't have to change. You just like rather than this way, yeah, just by like triangulating. Not really.